Today's going to be 62-2, and we're going to take a look at the real zeros of polynomials in Cauchy's Bound and Descartes' rule of sign. So today we're going to use Cauchy's bounds to limit the number of possible rational zeros and use Descartes' rule of signs to find the possible number of positive and negative real zeros. Now, one of the major issues of trying to find the real zeros of a polynomial is that there are technically an infinite number of possibilities we should try. Now, one of the theorems that we used previously was to limit those infinite possibilities, and we used the rational roots theorem to do that. Because remember, when we're trying to describe a polynomial, what we're trying to do is we're trying to find one of the elements is trying to find those zeros. Well, how do I find the zeros? We said that, well, if we know how to divide a polynomial, we can find those zeros. Well, how do I know what to divide by? We had the rational roots theorem to kind of help us determine that. But even still, we have a massive list of values that we're going to have to go through. So how do I narrow that list even more, or at least use a little bit of these techniques to kind of guide our thinking? And so we're going to go over two more theorems to help us limit those number of possibilities that we need to try, and the first is going to be Cauchy's bound. Now, what Cauchy's bound states is that suppose my polynomial here is of a degree n, where n is greater than or equal to 1, let m be the largest of those numbers. So of these numbers, and we take all the coefficients and we divide it by our leading coefficient. Whichever the largest is of those is going to be m. Then we say that all the real zeros are going to lie in this interval, bracket, negative m plus 1, and then m plus 1 bracket. So the theorem states that we should find m, then plug it into the interval. To find m, we take the absolute value of the leading coefficient and divide it into the largest absolute value of the remaining coefficients. So in this example here, it says let f of x equals 2x to the fourth plus 4x to the third minus x squared minus 6x minus 3. It says determine an interval which contains all of the real zeros of f. So to find m, I have to find what m is. I take the absolute value of the leading coefficient, so absolute value of 2. And then I look at all of my coefficients, and I take the largest one, and I take the absolute value of that value. So the largest is negative 6, so I take the absolute value of negative 6, which is 6. So I divide the 2 into the 6, and then I'm going to get 3. Then I take that 3, and I plug it in for m into my bounds here. And so I get negative 3 plus 1 and 3 plus 1, so my interval is going to be negative 4 to positive 4. So the interval in which all of my zeros are going to lie on is going to be this interval of negative 4 to positive 4. So the first thing that I did is I found m. To find m, you take the absolute value of your leading coefficient and divide it into the largest of the remaining coefficients. And so I got 3. Then you take that 3 and you plug it into the interval, which I did here, and so I got the bound negative 4 to positive 4. And so all of my real zeros are going to be in that interval. Next one, so I need to find what my m is, and so we said we need to take the leading coefficient, in this case it's going to be 1, and divide it into the largest of these, in this case is going to be 6. So 1 goes into 6 times, remember it's the absolute value of that, so that's going to be positive. And so now I'm going to take that 6 and I'm going to plug it in for m into each of these intervals. So I get negative 6 plus 1, and then 6 plus 1, and so that's going to give me negative 7 to 7. And so all of these are going to be the real zeros on that interval. Now just remember, one of the nice things about this is the fact that if I do my p's over q's, if I ever get a p over q that's outside that bound, ignore it. Also, I know that if I want to look at my graphing calculator and determine what my zeros are on my graphing calculator, I know that at least all of those zeros are going to be between negative 7 and positive 7. You won't find any zeros outside those bounds, and so it kind of helps us focus on our search when we're trying to do that. Now the next piece that we're going to take a look at is going to be Descartes' rule of signs. Now this says let your polynomial p of x written in descending order, ascending order. Now remember, descending or ascending order, what that means is you look at your exponent and your exponents are counting down. So it's 5, 4, 3, 2, 1, or it's ascending, so it starts at the lowest, like which is your leading coefficient or your constant, and you're counting up. So constant, something to x, x squared, x third, etc., etc. So be a polynomial with real coefficients and a non-zero constant term, the number of positive real zeros of p of x is either the same number of variations in sign of p of x or less than the number of variations assigned in p of x by a positive even integer. So whatever the sign varies, now what it means by vary is that it's going from positive to negative or from negative to positive. So if it varies, it's going to be that same number, or it's going to be less than that number by a positive even integer. So let's just say hypothetically it varied 7 times. So if it's less than an even number, that means I'm counting down by an even number. So it could be 7, or it could be 5, or it could be 3, or if it could be 1. I counted down by an even integer. And so I could have situations in which it could be any of those values there. Now you can't have negative zeros because it either crosses the x-axis value, like the x-axis, or it doesn't. There's no such thing as a negative zero. So that's something just to be aware of. And then the number of negative real zeros of p of x is either going to be the same as the number of variations in sign. So I'm taking that negative x and I'm plugging it into my p of x, and then count the number of times that that sign changes. Or it's less than that number of variations in sign in p of negative x. So you do the same thing. So first you plug that negative x in, you simplify it, and then once again, whatever that number is, you use that, and then you count down by an even number as well. Now a zero of multiplicity m has to be counted m times. Now it's kind of vague as to why I mentioned that. We're going to dive into that much further at a later lesson. Now if you're also wondering, why am I counting down by an even integer? That question will also be answered in a later lesson. So what information does Descartes' rule of signs tell us about the polynomial? So with my polynomial, we said that we have to count the number of times the sign changes. So positive to negative, negative to negative, negative to positive. So there were 2 variations. Then we have to take that 2 and count down by an even integer. So 2 minus 2 is going to be 0. So the number of possible positive zeros is either going to be 2 or it's going to be 0. Now to find the number of negative zeros, or the possible negative zeros, I have to do p of negative x. So that means you take negative x and you plug it into your function. So 2 of negative x to the 5th minus 5 negative x squared minus 3 negative x plus 6. Now that I plugged in that negative x, now what I need to do is I need to simplify that. So I have an odd number of negatives, so negative and a positive gives me negative, an even number of negatives, so it stays the same, odd changes, stays the same. And then once again, now I need to count the number of zeros that are going to be represented there. So negative to negative, no. Negative to positive, that's a variation, positive to positive, no. So in this case, I have 1. Now if I count 1 down by an even integer, 1 minus 2, that gives me negative, so I don't count down anymore. So I only have 1 possible negative zero. Now how do I interpret this information? If I have my p's over q's, there's a chance that 2 of those p's over q's are positive, or none of them are. Or another way of thinking about it, if I look at it on a graphing calculator, there's a chance that 2 of those, it's going to cross my x-axis twice, or it's not going to cross it at all. But I know for certain it's going to cross the x-axis in the negative region once. There's a chance it won't cross here, definitely will cross here. So when I do my p's over q's, I should start with my negative zeros, because there's a definite chance that a negative zero is going to be there. So the first thing that I did is I counted the variation signs of p of x. So that's what I did here. I determined that there were 2, and then I counted down by an even integer, so 2 minus 2 gave me 0. Then I count the variations of the sign of p of negative x. You have to simplify it, so I did that, and there's only 1 variation in sign. And so that 1 variation in sign gave me 1, and then you count down by that even integer as well. Well, 1 minus 2, that still just gives me 1. And so I got 1 possible negative 0. And remember, this is referring to the number of zeros. Next example. So first thing, count the number of variations in sign. So positive to negative, negative to positive, positive to negative, negative to positive. So there's 4 variations in sign. Now I need to count down by an even integer. So 4 minus 2 and 2 minus 2 is 0. So I get 4 minus 2 is 2, 2 minus 2 is 0. So there's a chance it's 4 positive zeros, or 2 positive zeros, or there aren't any positive zeros at all. Then, step 2, count the number of variation signs of p of negative x. So I plug in negative x into my function. Now I need to simplify that. So if I simplify that, that's going to stay the same, change, stay the same, change, stay the same. And so now counting it, nope. See, there's no variation at all. So I know for certain there are 0 negative zeros. There are not any negative zeros here. So when I do my p's over q's, I should only test my positive p's over q's because I know for certain that there aren't any negative zeros here. Now to conclude our lesson, we did talk about Cauchy's Bound and the Descartes rule of sign. Now for Cauchy's Bound, to find m, what you do is you take your leading coefficient, you take the absolute value of that, and then you have to find the largest other coefficient. So you look at the other coefficients, and you take those, and you take the absolute value of that, and that's going to be your m. And then now for the third question, it says if I use Descartes' rule of signs and I determine that I have 1 possible positive zero and 2 or 0 possible negative zeros, which types of zeros should I try first and why? Well, because I know for certain I have 1 positive zero, I should test my positive p's over q's first because I know for certain that I'm going to have one. There's a chance that I have 0 negative ones, and so because there's a chance I have 0 negative ones, I want to try those last. So this does conclude our lesson. If you do have any other questions, please leave them in the comments.